we are worried about whether this is preserved to be done. So you write this report document. And then we proved after that every distance preserving mapping from a metric space to another one is injective mapping. Right? Is it difficult? You understood the proof, right? Although I was reading the slides only. So the one statement is that here is that if F is distance preserving any mapping, but as soon as it preserves distances, then it becomes automatically injective mapping. I have joked about school teachers or university lecturers there because X1 is not equal to X2 implies Fx1 is not equal to different elements, some of the different elements, which means if the image is the same, then original element must be the same. That is used by using the first axiom of the matrix spaces to prove this. Second concept is isometry. This condition, exact condition is that it is distance preserving and bijective. Bijective mapping is the concept that can be nicely defined in descriptive mapping. For example, I taught descriptive mathematics something like 20 times, and I have a book. You can actually download it from Amazon. In that book, the mappings are very rigorously treated and relations. So that if a mapping is bijective and it preserves distances, then we call it isometry. Call it an isometry. And now we look at the same space. Y is equal to X. So we are looking at mapping from the space to itself. Isometry is from X to X. But we're now looking at not only one mapping, but all of the mappings which are isometric from X to X. So, under the same distance, of course, X can have different distances. And these are the set of all isometries from X to X is denoted by isom X. You can put the brace down, but you don't have to. You put a space somewhere here if you're typing later. This isom is a group. Under composition of mappings. I'm not going to not write everything or display that, just say through it. First of all, you need to group, a group is a non-empty set with a binary operation on it. The binary operation satisfies three conditions. One is associativity. If you have mappings F, I will drop the quantifier there. If F, T, S, H are all from the set, we are not saying these are distinct. They can be all equal or some two of them might be equal. We're taking arbitrary three elements from this, and then it must satisfy that whichever two you do first give the same result if you don't change the order. That is what the associativity says. You have to imagine in your mind that the multiplication of numbers or addition of numbers, you add these two first and then add that one gives you the same result as if you add these two first and then add the result on that one. So this is what it says. First condition. Second condition is there exists an identity element. 1 is here. I always use this same 1 because I will not have a occasion that this 1 is used for 5 different things on the same plate. In which case mathematicians can tolerate if you don't use more than 3 times same symbol for 3 very different concepts. This satisfies its own axiom. This axiom is not for every x. Every f, let us say, in isom. F combined, first use identity mapping, then use it coming from here to there, then use F mapping to F, it's the same as F itself, or if you first apply F and then apply identity. This is what is meant to be called the identity, axiom for identity. The third condition is inverse element. Every element is invertible. For every F in isom X, this isom X can be replaced by any G, which gives you the abstract definition of an abstract group. Here we are using this because we are now talking about isometry. There exists an element G. This exists. That one is every. In the same set, such that either way you apply, either 2 of the ways you apply these 2 mappings, you get identity mapping. This is called the axiom for the inverse element. And as soon as this is done, you can easily prove that identity element in any group, any abstract group is unique, and inverse element of any given element is unique. It's just the application of these axioms. There, if this is unique, then we just write it as F inverse. Why is isometry invertible? Because it's bijective, therefore there must be an inverse mapping. That inverse mapping also preserves distances, and then you verify that the inverse of an isometry is an isometry. Okay. What did we do after this? We proved that this is a group, and this is about the same idea. The axioms are the group is not written down. You have to understand. You have to go through it carefully and understand. It is not necessarily abelian. Abelian means if a group is abelian means the binary operation is commutative. Commutative means whichever you write first for 2 composition of 2 elements, whichever you write it first, it gives the same result. But here, if the space X is very special, such as Euclidean spaces, you can probably prove that they verify that the group of isometries is also commutative, abelian. And I was saying in the beginning that we should do a good example here, and we didn't do last time. We should choose an example and do it here. What is our beginning point? Where did this metric space concept arise? Where did it get born? So we will go there to the mother and then ask her, how are you, and so on. Where did it get born? It was born in Euclidean spaces, isn't it? Because Euclidean distances is very natural. So we consider Euclidean spaces. Example. I think I'm going to erase that and go back on there. Example.
Should we put down the other mode also?
Yes, if possible. We are probably not using that one today. We will do slowly because
Oh yeah, I would do that.
I have been told, I have been advised by Dr. Fahim that we should go slowly and try to interact more. This I usually tell us if you are eating something, very good meal, like what we are having here. if you eat it slowly and digest, then it is good for your health. If you have very good meal or very bad meal and then you eat too quickly, and 5 meals, you eat all the meals which you are going to eat until the New Year, today, then you might, it is damaging to health. So let us, instead of trying to cover everything, we will try to digest everything. And wherever we reach, it doesn't matter the remaining ones you will read. And this also makes it easier to write exam, because exam will not cover the contents which are not covered in the lecture, right? It's automatic. Is that agreed? And I think you are going to give a certificate after you take the exam, whoever who wants it, from the school. So this is all administration. So let us consider Euclidean spaces. I don't want you to imagine that where we are sitting is an Euclidean space. It is not, in my opinion, but maybe Einstein or Govt told you that it is somehow locally Euclidean or something like that. So what does Euclidean space say? Let n be a natural number. Then Rn. This is the Euclidean space. You must have done this in linear algebra, Euclidean space. And we're going to consider this not only as an example, but this space will we will live with it, not in it. We will live with it. It is in our imagination actually, but may not be her imagination. So what does it mean by Euclidean? First of all, it is a vector space over R. Right? This has how many axioms? 8 axioms are there. Vector addition gives it as an abelian. Scalar multiplication satisfies certain axioms, and together it's actually a module axiom. So first of all, Rn is a vector space. It's finite dimension, and dimension is n. On top of that, there is just one definition added, introduced, which is natural. Not only, maybe in this sense we're calling mathematics natural science, maybe, I don't know, because I never regarded mathematics as science. Do you regard mathematics as science? It will go to a long discussion because it's something very close to religion or philosophy. Something else is introduced in it naturally. What is it? 2 words. An inner product.
Yes.
Inner product.
An inner product, we temporarily write it as, for 2 vectors, we write it as this, which satisfies several conditions, some of which are summarized as bilinear, some of which are summarized as scalar emitting or something. If there is one scalar here or there, then it goes out. Is that right? Bilinear means this one is linear on that one is linear on that. And this can usually be obtained by, if this is a vector, let us say this is a column vector of dimension n, it is written from top to bottom. Then we are looking at, this is given by, in that, after coordinatization, you transpose it and then you multiply by u. What does it mean? This one is a column. That one is, after transpose, it becomes row. So you're holding this column there, another row there, and you slowly rotate and put it on juxtaposition, and multiply the corresponding entries and add it up. That gives you a number. That number is called inner product. This is all familiar to you, right? You should really know it by hand, not by head, just head. You should know it by hand. And let us now consider, this is a matrix with this. Now here, this condition here can be written down as inner product is preserved. So if F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R into itself, then F is a mapping from R f of u, f of b, u, v are any two vectors. It's the same as the inner product of u, u of b. This condition is that condition written down in terms of inner product. And you can immediately prove that. What can you prove there? Inner product is preserved if and only if length of vector is preserved. Length of vector. Which is norm, but many functional analysts call it normal. We don't need to really advertise ourselves like we know norm and more than length. I usually just use the Hamburg word length. Norm is fine. Norm is preserved. So you can easily prove that the inner product is preserved by a mapping if and only if norm is preserved by a mapping, if and only if distance is preserved by this mapping. This is an exercise question. I should really write it down the exercise. Exercise question. I can prove it here now, but we have to walk a little bit. F from Rn to Rn is the mapping. This, if and only is that, if and only if one is already used. Raise two. Raise two. Prove that one if and only if two. If and only length of Fu is equal to length of U. Is it very difficult? I don't believe it is.
No, you can understand.
I don't believe it's very difficult to anyone. So that is one of the. Though I like that you go to internet and search and try to understand it, but try to write down it first yourself, and then you can go to the internet and compare. And one thing about internet is that I found many false proofs and errors in internet, except maybe Wikipedia, but Wikipedia also sometimes makes mistakes. So this is one exercise. Now, my question. What is the group of isometry of I? What does it look like? So last time I was writing for any given metric space, determine the group of isometries. Some my girl students misunderstood it because she said you're asking us to prove it is a group. No, it is a group already. For any given, this is the one example. Rn is a very good metric space, right? Euclidean space is very cubical and it is the birthplace of metric geometry. What is the isometry? What are the isometries? We all need to do is we just stick to one of these equivalent conditions and verify. Now, first of all, if F is an isometry of I, can you quickly prove that it is linear bijection? It's actually orthomorphism, linear orthomorphism. The crucial thing is a linear mapping. And bijectivity is already in the definition of isometry. So it's a linear isomorphism. If it is a linear mapping, then it is a linear isomorphism. How to go about proving this? It needs a condition. In isometry and zero vector is mapped to zero vector. So the zero vector is fixed. Of course, if zero vector is not fixed, for example, you could if you have a line segment, if you translate it in any direction, its length doesn't change, right? Because you shouldn't be thinking like physicists. Einstein would say, if you move it too fast, then this side the length will be increased or shrink. Because the line segment doesn't have any thickness, so or if you're moving this too fast that way, don't think in reality. In mathematics, translation means any addition of any vector. It doesn't matter how large that vector is and how quickly we add. It doesn't depend on it. So how can we prove this in this exercise question 2? You need to prove it. And it's all online. Of course, this is exercise question 1.
Okay.
This is exercise question 2. What is the linear mapping? Linear mapping means it's preserve the sum of the image of sum of vectors is sum of the images.
Yes.
Image of scalar multiplication of a vector is scalar multiplication of the image. Or you can write it in one identity like A U plus B V F under MF is equal to A times FU plus B times FB.
Yes.
Better do it in 2 steps in this case. So this is true. This is true. Now, let us apply this condition. And we know that this condition, this inner product can be written like that. So let us have a look at what happens if F is an isometric of F. This is assumed to be true already. In isometry. Being linear, it has a what does it have? Being linear means that if you choose a basis of this space, it can be written as an invertible square matrix. So, and let A, E, the matrix. This is n by n matrix. Bijective means invertible. Matrix of F under fixed basis. If you change the basis, your matrix will change. But if you, for example, if you look at the standard basis, then you have your matrix quickly covered. And we look at this condition, this condition. So this is equal to, even if you put get u will be any 2 vectors. Then by definition of isometry, what is happening is that the triangle bracket of U, AU, must be equal to UV. But what is triangle, what is left side? Left side is given by transpose of the first multiplied by transpose of the second juxtaposition. So this gives you AU transpose times AU. Now this transpose of any 2 matrices which can be multiplied, you have this linear algebra basic thing. What will happen? The result is they change, transpose, it change places, right? Okay, so this is equal to U transpose, A, V. But what is this side here? This side is just U transpose, V. Now this means that that matrix is identity.
Yes, sir.
What does it say? The transpose is the inverse of it.
Yes, sir.
Transpose is the inverse of the matrix is the definition of
Orthogonal.
orthogonal. Very beautiful, short, easy, and you get now every isometry is an orthogonal transformation. Orthogonal linear transformation. Of course, orthogonal transformations are all bijective, by the way. And then you can easily also prove that every orthogonal transformation preserves themselves. Doesn't it? Because it's determinant has absolute value 1. It determines it either 1 or negative 1. In either case, the vector length is preserved, or inner product is preserved. Which means every orthogonal matrix is also an isomer. Every orthogonal transformation. This should be taught in linear algebra. On the other hand, every orthogonal transformation fixes the origin and preserves the inner product. This crisis or inner product. So we proved that you know the set of all orthogonal transformations under composition of matrix is called something. It is the orthogonal group. So the orthogonal group and the isometric group are the same thing if it fixes the origin. The last summary of this is that isom I, which fixes the origin, here's the condition I fixes the origin. Is equal to O N R. The orthogonal group of index R over U. All digits. Very beautiful subject. What does it actually look like? For example, if we only consider vectors of length 1, their length is all preserved. What is happening? Vectors of length 1, their endpoint, they start on the origin, their endpoint is on what? Unit sphere in I.
Yes.
And orthogonal vectors will preserve, mark these vectors to themselves because it has to preserve length. Which means that all continuous motion of S2 is also this group. Let me narrate. The group of all continuous motions, the continuous group, is topological group. Of motions of S3. S2. S2 is x squared plus y squared plus z squared is 1.
S minus 1.
Huh?
S is for n minus 1.
Yes. Its own dimension is 2. The ambient space dimension is 1 more. It has a clear expression here. X, Y, Z. I'm writing this probably for the third time now. 3, because it's 1 to 3. Their squares, sum of their squares is 1.
Yes, sir.
And this is the algebraic, affine algebraic, real algebraic variety as well. My question in the first initial lecture was determine all the rational points in that. And we were working on this unit circle, two or three of you are working on this unit circle quite a lot, searching internet and trying to understand the thing. Even this is very beautiful and simple and very important as well. What is the next? Is next class of. Let me give some more examples, because examples are really appreciated usually, and you don't need to really teach theorems. You can teach only examples like many universities in the United States. It is just a tutorial session, in my opinion. But yeah,